Assalamu alaikum everyone, this is Fahad Ansari and I'm here to help you conquer chemistry. So in the last video we looked at isotopes in detail. So in this video we'll start to look at the arrangement of electrons within atoms, which is known as electronic configuration. So you guys are aware that the nucleus consists of protons and neutrons, whereas electrons are arranged in these fixed energy levels, which are known as shells. Now these shells are denoted by a certain kind of number, which we call the principal quantum number. Now the principal quantum number in simple terms is a fancy word for shell number. So shells are basically numbered from 1 onwards depending on how close the shell is to the nucleus. So this principal quantum number or shell number is denoted by n. So n can have any value from 1 to 2 to 3 and onwards. And this 1 represents the shell that is closest to the nucleus, followed by shell number 2 and then shell number 3 and so on and so forth. So these shells over here can hold a maximum number of electrons depending on how close the principal quantum shell is to the nucleus. And this maximum number of electrons is given by this rule over here, 2n squared. So for example, if we have shell number 1, then the maximum number of electrons that first shell, the shell that is closest to the nucleus, can hold is 2 times 1 squared, which gives us 2. And then shell number 2 can give us 2 times 2 squared, that gives us 8 electrons. That's the maximum this shell can hold, followed by the third principal quantum shell with a maximum of 18 electrons that it can hold in that principal quantum shell, with the principal quantum number n equals 3. So these principal quantum shells further consist of subshells, which further consist of orbitals, and then within the orbitals you find the electrons. So molecules are kind of like Russian dolls. So within a molecule you get an atom, within an atom you get a shell, and so on and so forth. So basically you keep opening up and splitting atoms into their multiple parts, and then you get parts within parts until you get to this little doll over here, which is the electron. Now let's talk about subshells. Now there are 3 kinds of subshells that you will encounter in your AS level course, which are the S, the P, and the D subshells. Now the S subshell can hold a maximum of 2 electrons, the P subshell can hold a maximum of 6, and the D subshell can hold a maximum of 10 electrons in that subshell. Now each subshell consists of 1 or more orbitals. Now remember that an orbital can hold a maximum of 2 electrons. Now this orbital could be in an S subshell, a P subshell, or a D subshell. In either case, the orbital can hold a maximum of 2 electrons. So keeping that in mind, the S subshell only has 1 orbital, which holds the 2 electrons in that S subshell. And in the P subshell, we have 3 orbitals, each of which holds 2 electrons. And then we have 5 orbitals in the D subshell, each of which holds 2 electrons, to give a total of 10 electrons. So this was about subshells. Now, getting on to the shapes of these subshells, or rather the orbitals within these subshells, we're only going to be looking at the S subshell and the P subshell and the orbitals that they contain. The D subshell and its orbitals are part of the A2 chemistry course. So the S subshell has only 1 orbital, and that orbital looks like this. So this shape is spherical. Now on this flat screen you might think that this is a circle, but it's not. It's a sphere. And we denote this sphere being a sphere and not a circle by using these axes over here, x, y, and z, to show that we are talking about a figure in 3 dimensions, so it's a sphere. All right, and at the center of this spherically shaped s orbital, we have this nucleus right over here, the center of the atom. All right, now the p subshell has a different shape for its 3 orbitals. Now one of its orbitals is shown over here. Now this shape is usually called a dumbbell shape, or some people like to call it the hourglass shape, and some students say that it looks like an infinity sign. Well, infinity sign again is a flat shape, it's not 3-dimensional. So it's better to call it either a dumbbell or an hourglass shape. All right, we have a nucleus at the center, as always, and this particular p orbital is lying on the z-axis. So we're going to call this the pz orbital. Now the orbital lying along the x-axis would look something like this. So we're going to call this px, and the py orbital is going to get a little messy, but here we go. We have this orbital over here, which is py, this is px, and the one that you saw earlier was pz. All right, so there are 3 orbitals in the p subshell, 1 along each axis. Now each of these orbitals, remember, holds 2 electrons. All right, so we know that the principal quantum shell with the principal quantum number n equals 1 has a maximum capacity for 2 electrons. So that means that it only has one subshell, which is the s subshell, which can also hold only 2 electrons. When n equals 2, we know that that principal quantum shell holds 8 electrons. And that means we have an s subshell and a p subshell. Now the s subshell holds 2 electrons, the p subshell holds 6, so 2 plus 6 gives us 8. And the third principal quantum shell, which is further away from the nucleus, and it has a higher energy level for the electrons, has 18 electrons that it can hold. So we have s, p, and d, all 3 subshells. So the s has 2 electrons, the p has 6, and the d subshell has 10. So 2 plus 6 plus 10, that gives us 18. Now that we've looked at subshells and orbitals, now let's move on to actually writing electronic configurations. But before that, we need to cover one very important thing, which is the Aufbau Principle. So the Aufbau Principle basically states that the subshells are filled in ascending order of energy level. So the subshell, not even the shell, the subshell with the lowest energy level will be filled with electrons first, followed by the next subshell and then the next subshell. Now, how do we determine energy levels? Well, a rough idea of relative energy level of the subshells can be found by listing down the subshells like this. Now, for example, 1s basically means that this is the s subshell of the first principal quantum shell, and then we know that the first principal quantum shell only has an s subshell. Now in the second principal quantum shell we have an s and a p subshell. So for the second principal quantum shell we have an s subshell and a p subshell, so 2s and 2p and so on. Now what we're going to do is we're going to add the principal quantum number n for each subshell over here, and we're going to add that to the number L. Now L is basically the angular momentum quantum number, Now this is another fancy term, and in simple words, this just means subshell number. So N is shell number and L is subshell number. Okay, so for the S subshell, we have the number 0, for P we have the number 1, and for D we have the number 2. So these are the values of L, the angular momentum quantum number, or the subshell number for S, P, and D. So for example, for the 1s subshell, N equals 1 and L equals 0. So 1 plus 0 gives us 1. So for 2s, N, the principal quantum number, is 2. That's the shell number. And then the subshell number for the subshell S is 0. So 2 plus 0 gives us 2. For 2p, that's 2 plus 1 equals 3. Right? Now 1 over here is the value of L for the P subshell. So 3s gives us 3 plus 0, that is 3. For 3p, we get 4. For 3d, we get 5. For 4s, we get 4. And for 4p, we get 5. All right. So now these sums over here give a relative energy level idea to us. Now, the 1s subshell has the lowest energy level and it has the lowest sum. 2s then has the next lowest energy level and the next lowest sum, followed by 2p. Now 2p and 3s have the same sum. But we will know that the 3s actually has the higher energy level, and the reason is it has the higher principal quantum number n, right? So over here 3 is greater than 2, so it has a higher principal quantum number, so that's why we know that 3s will have the higher energy. Now over here you can see that these two need to be swapped in the list. So we know that 4s is a subshell with a lower energy level and 3d has a higher energy level because of the difference in their sums. And then once we replace these, once instead of 3d I write 4s over here and then I write 3d over here in the correct order, and their sums are swapped as well. So you will see that the sum for 3d is 5, right? So over here if I write 4 and over here if I write 5, you will see that this 5 and this 5 are the same, but again, in this case and in this case, we know that 4 is greater than 3, the principal quantum number is greater, so 4p has the higher energy level. So this is one way in which you can arrange subshells in order of increasing energy level, and this is important in writing electronic configurations. Now we have this list over here according to the Aufbau Principle, and we're going to be using this list to just do some examples of electronic configuration. Now the oxygen atom has 8 protons, so it has 8 electrons. So now we're going to write its electronic configuration like this. So the first subshell with the lowest energy level that will be filled first is 1s. Now this s subshell can only hold 2 electrons, so we will write a small 2 over here. So 1s2 means the s subshell of the first principal quantum shell has 2 electrons in it. All right. Now this is followed by 2s, and it has 2 electrons, 2s2, and then the next subshell is 2p according to the list, according to increasing order of energy level. And we have so far assigned 2 and 2, that is 4 electrons. We have 4 more electrons, so those 4 will go to 2p. We know that the p subshell can hold a maximum of 6. Over here, this p subshell is partially filled. So 1s2, 2s2, 2p4. That is the detailed electronic configuration in terms of not just this principal quantum shells, but the subshells as well, right? Normally, you would write the electronic configuration of this as 2, 6. That's 2 electrons in the first principal quantum shell, 6 in the second principal quantum shell. Now over here, it says that the 6 electrons of the second principal quantum shell are divided such that 2 of them go to 2s and the remaining 4 go to 2p. As another example, we have the sodium atom. So its electronic structure or configuration or distribution would be 1s2, 2s2. Now we have 4 electrons assigned, 2p6. Now that gives us 2 plus 2 plus 6, that is 10. And we have 1 electron remaining. We have filled the 2 electrons in 1s, 2 electrons in the 2s, and 6 electrons in 2p. So now the next subshell is 3s, and the 3s has the 1 remaining electron. So 2 plus 2 plus 6 plus 1 gives us a total of 11 electrons. That is in the sodium atom. Now the neon atom has an electronic configuration of 1s2, 2s2, 2p6. 2 plus 2 plus 6, that gives us 10 electrons in the neon atom. All right. Now, in order to shorten electronic configurations that get too long by this method, we could replace the beginning part of an electronic configuration of an atom or an ion by the symbol of a noble gas. So for example, the sodium atom, you could see this first part, 1s2, 2s2, 2p6. It is the same as the electronic configuration of a neon atom. So if I replace all of this by the symbol of this noble gas neon in square brackets, and then write the remaining part over here, 3s1, it is also acceptable. And it saves us a lot of time. So you could write this as well. So if you have an atom or an ion, then you could replace the beginning part of its electronic structure or configuration by the symbol of the noble gas in the period before that element in the periodic table. So for example, for the oxide ion, we have 8 protons. This 2 negative charge tells us we have a total of 8 plus 2 equals 10 electrons. So the electronic configuration for the oxygen atom was this, 1s2, 2s2, 2p4. Because this has 2 more electrons, and we know that the 2p subshell can hold a maximum of 6, right now it has 4, so the 2 extra electrons will go to the 2p to fill it up. So it'll be 1s2, 2s2, 2p6. Now this electronic configuration is the same as that of neon from the beginning to the end. So we can just write this as Ne in square brackets. It tells us that the ion has gained a noble gas configuration. And the sodium ion, 11 protons. This positive charge tells us that we have 1 less electron. That gives us 10 electrons. So same as the number of electrons in an oxide ion. So this will also have the noble gas configuration of neon. So we have simple electronic configurations that we have done so far. And in the next video, we'll be looking at some more examples of electronic configuration. And I hope you did like this video. If you did, please leave a like and do share and subscribe to the channel. Inshallah, I will see you in the next video.